Designing chips today requires a significant amount of emulation. The chips are getting extremely large, so there are a lot of challenges in terms of developing these systems. So to start with, what are some of the changing demands in the chip emulation market these days?
The changes are actually quite simple. The customer are facing tremendous challenges related to the large device that they have to do and the very long software workload that they have to execute. So that means they need more speed. The workload that they have to verify are very long, very time consuming, and their designs are scaling to be very, very large. So they need capacity. And both emulation and prototyping are really addressing very well the speed and capacity dilemma for our customers.
Okay. So what are the trends in chip design these days?
The trend in chips design is, I will say, in 2 dimension, or people say 2 or 3D. One is in the logic die level. Moore's law is not dead. It's very vibrant. We see more and more customers that the logic piece is at the largest reticle size allowed. And then there is these 2.5D or 3D integration in the other dimension where they can stack different type of dies or application so that they compose a complete system here in the package. That's really the trend that we see, and it's very vibrant. There's a lot of improvement that have been made in the 2.5D 3D technology. We are using this ourselves for our own crystal chip.
What are some of the other aspects that are controlling how chips are being designed these days?
We see a very clear trend with what we call AI or custom accelerator. A lot of system companies, they have a very specific need. They have defined a particular workload that they need to execute fast, or the chip needs to perform within the system they are selling. So they are not selling and serving a general broad market. They are trying to design a specific custom accelerator. It can be AI, ML, doesn't have to be, but sometimes most of the time it is. And they really do a chip that has only that function. And they verify that chip within the system requirement only of the function that they have. They don't care about serving a generic CPU or GPU market. They care about doing a custom accelerator for their own system function. And that's a trend that we see that is very clear.
So what are some of the major apps or approaches that are defining these requirements? Hyperscaling, for example, comes to mind.
Hyperscaler is very clear. They have a well-defined function that runs usually on a data center, and they need to have an optimized, accelerated function. So for that, they have 2 options. Either they buy generic CPU or GPU and they architect the function that they need to accelerate, or they design themselves the chip to do that specific function. It's very similar to the ASIC world 20 or 30 years ago. The market started to talk about ASIC because it was a very specific purpose piece of equipment or piece of silicon. It is the same concept. They know what they need to accelerate, and they have options to do generic parts, which has certain consequences, good or bad, or their own custom parts, and they do the investment of defining the requirement of the chip and design the chip to fulfill the requirement.
It sounds a lot like the software-defined vehicle requirements as well.
It is very similar to software-defined vehicle. So SDV is the term that is used a lot in the automotive market, but it's applicable to not only automotive. We see that in many, many different markets. But the concept is quite simple. There is a software requirement and trends, and that's most of the first thing that people see in a car today. Is when they arrive inside the car, they look at the console and what the software experience is. What the car experience is kind of secondary now. The software experience inside the car, what drives how the car is going to be architected, and that's why we say by software is eating the world. And they start from this concept and they define what chip or system needs to do to execute very well that software application. Prime example is Tesla. Tesla has done its own chip. The FSD chip is the perfect chip for the Tesla car. If you take that chip in another car, it's not going to work. So it is really a piece of silicon that is done based on what the software, the system software requirement is. And we see many car makers going in that direction. They define what the software is, and then they define based on the software what the underlying electronics architecture and piece of silicon will execute.
Okay, now emulating the systems actually requires different levels at this point. You've essentially defined three. Could you tell us what they are and who's going to be using each one?
So we see really three, I don't want to say bucket, but solution space that are complementary of each other, but they are distinct. There is really a need at the beginning for what we call a hardware emulator. And that's early in the stage of the design, realization, and verification of a chip. This is close to architecture, where you have also a link to virtual platforms. So you make decision on what architecture you're going to select, IP selection, and you start to assemble your SoC RTL. At that time, this is very heavy in compilation and debug. A little bit less on performance because the thing is the RTL is not stable yet. So you need to compile very often, change the design, and debug the design. And that is really the requirement envelope of what the emulator and the emulators that we are offering today is defining. And then when you're done with that point of the RTL is what we call stable, you are less in debug hell. You are in acceleration. You want to run longer workload, and you want to run a bit more software content. So here you need a congruent hardware from the emulator that allows you to move this design very easily from the emulation environment to the enterprise prototyping environment. And you run and execute, because the system is faster, longer workload and more software content. And you have less debug. But if you find problems, you can, with the congruency, go back to the emulator, back and forth, and debug like this. So that's those two solutions are also, from a hardware perspective, different. They are very complementary and congruent of each other. And you have the third space that is really more software system. This is where you are as close as possible to real-time execution. So your peripheral are really, in a way, connecting to real hardware target, real board. And for those, it's maximum speed that you can get. You take a little bit more time to what we call cable or set up the design, but then you get the maximum speed, and you need to be able to scale very well from a single FPGA to multiple rack of FPGA. And that's really the three solution space that we see that most of the large semiconductor or system houses, that's what they need today. They need to have a complete offering that has a very good software congruency behind it, but also have a hardware that is very flexible, very scalable, and very reliable.
So from a product perspective, how is Siemens now addressing these different levels of emulation?
So this is the first time that we are actually offering three hardware at the same time. Historically, we had a different schedule. And the three hardware are the emulator called Veloce CS. And this emulator is really today the fastest and the emulator that is the only one able to do up to 40+ billion gates. The second is Veloce CS, which is our enterprise prototyping, very congruent from CS. From a hardware perspective, they look exactly the same. And the software is quasi identical, except the place and route. And it's allowing to scale at the prototyping level very easily from the emulator and get a 3 to 5x improvement in speed versus CS, and half the cost per gate, roughly, being on the enterprise prototyping with CS. The third is called Veloce Pro FPGA CS, which is the next generation of our Pro FPGA. And it's really targeted to what we call software prototyping, where this is the fastest prototyping environment that you can get, where you have the highest flexibility to use the customized I/O from the AMD FPGA chip, from a single FPGA, which we call a Uno board, all the way to a quad, which is 4, and then Xi, which is 6, which we put inside racks, all the way to roughly 12 billion gates or 180 FPGA devices.
Well, very good. Thank you for filling us in on Siemens' view of the changing chip design market.